All right, in this next section, section C4, we are going to be looking at doing some arithmetic in binary and hexadecimal. So we are so accustomed to dealing with arithmetic with these algorithms that we learned back in like second, third, fourth grade for doing addition, subtraction, multiplication, etc. Now the thing is, computers on a fundamental level, as we mentioned, are dealing in binary, or programmers might be programming these things in terms of hexadecimal, which then gets easily translated into binary. And all of the rules that we've learned for doing addition, subtraction, etc. had to do with the specific way that the decimal numeral system works. So what we're going to see is that there's actually, because these two systems are still positional numeral systems, right, place value systems, they're going to have similar rules, but they're going to have slight variations. And because we're so used to doing things in a very particular way with arithmetic, we're going to have to relearn how to do some of that stuff. Let's first start with a couple of warm-up questions. We've done binary numerals now for the last few sections here. We can ask ourselves what binary numeral is going to be the successor, or the next number, for the binary numeral 1, 1, 1. Remember, this means we've got 1, 4, 1, 2, and 1, 1. If I want to figure out the next number, well, that's 7, so it's going to take me up to 8. If I want to represent that next number 8, I'm going to need to have another digit here to represent that. So the next number is going to be 1 followed by 3 zeros, and that's base 2 that we're talking about here. What's another way we could think about writing that? This is telling me that if I take 1, 1, 1, and I add 1, right, that's what it means to take the successor, the next number, is you add 1 to what you just had. It means that what we get out of that is going to be a 1 followed by 3 zeros. So we're going to have to talk about what are the rules that let me conclude this, right? This does not look like the familiar way that we'd use to do addition. But in a certain sense, it is kind of similar, right? We line up the numbers in a certain way, and then what we're going to have to do is think about adding them like a column. So we're going to align the numbers vertically such that the rightmost digits are going to be aligned. So that way we're thinking about adding ones together, thinking about it back in decimal. Like you add the ones together, you add the tens together, you add the hundreds together, and so on and so forth. And then remember the way that this works is we start with the smallest denomination, and we add from right to left. Right, so just to do a quick decimal example, right? If you have, say, 73 plus 48, we remember how this works, right? You add the 3 to the 8. Well, the problem is 3 to the 8 gets you 11. I can't write 11 in one digit, right? So I have to write the 1 down here, and then remember what we have to do is, quote, carry the 1, which really meant we're sort of making change, right? 3 plus 8 is 10 plus 1. So I put the 10 over here, the 1 that's left over here, and I've got 1 plus 7 plus 4. Well, that's 12. Well, again, I have to make change here because only the 2 can go right there, and then the 1 goes over there. So that principle that we learned way, way, way long ago is the exact same idea. We just have to retrain our brain because all of these digits, except for the 1, don't exist in binary. The only thing we can do are zeros and ones. So if you ever add up digits and the sum is greater than 1, we have to sort of carry the 1. We have to basically convert it. Let's look at how this works with just a few small examples and then talk about how to do a more complicated example. There's 5 basic rules we need to know to be able to add two binary digits. 0 plus 0, no surprise, is 0. 0 plus 1 and 1 plus 0 both get you 1. Now 1 plus 1 is 2, but 2 is not a digit in binary. So we have to write 2 the only way we know how in binary, which is to convert the 2 into a 1 on the left space, right? So we basically have to push it over in the exact same way that we did over here. When we get to a number that's bigger than 10, we convert that 10 in the value to the left spot. Well, in binary, the digits that are to the left aren't 10 times as big, they are twice as big. Last thing we'll need here, 1 plus 1 plus 1. Well, again, we already said that 1 plus 1 was 1, 0, right? Now if we add another 1 to that, we add 1 to the digit of 0, and we get 1. So, and remember, all I'm saying here is that 1 plus 1 plus 1 is 3. It's just that in binary, 3 is going to be represented as 1, 1. So let's find the sum of these two binary numerals, 1, 0, 1, 1, 0, and 1, 1, 1, 0, 0. All right, first things first, we're going to align them vertically such that the rightmost digit is aligned. Well, these numbers are, they both have the same number of numerals, so that's easy. So I'm going to add column by column. So the rightmost column, not much interesting going on there, right? We've got 0 and 0, that adds up to be 0. Next up, we've got 1 plus 0, that equals to 1. Now we've got 1 plus 1, but remember, we can't use 2. 2 is not a thing in binary. All we get are zeros and ones. So we have to use the fact that we noted here. 1 plus 1 is 1, 0. So we're going to put the 0 down here, and then the 1 is going to get carried over to the next column. So in that next column, we've got a 1 and a 0 and a 1. Well, 1 plus 0 is 1. Add another 1. That also gets us to 1 plus 1 is 1, 0, right? So we have to note that we put a 0 down here, and we carry the 1 over to the next spot. Now, the very last thing, we've got 1 plus 1 plus 1. Well, we noted that is equal to 1, 1, which is the binary for 3. So in the column that we had, we're going to put a 1, but we still have another 1, so that one's going to have to go further to the left. Again, it's much like what we saw in that example up there. If we add 2 digits, we might end up needing another digit to express, if we add 2 numbers, we might need more digits to express the resulting sum that we have here. This might feel very, very, very foreign, so let's check by converting these numbers back into decimal, which hopefully you've had a chance to work through the homework, so this feels a little bit more familiar, right? We've got here, that's my number of ones, right? So I've got 0, so that's my number 2, so 2 plus 4, nothing there, and then 16. So 2 plus 4 plus 16. So this binary numeral represents 22. This binary numeral down here, again, think about it right to left, 0 plus 4 plus 8 plus 16. So this binary numeral represents 28. If I do 22 plus 28, this feels more familiar, right? 2 and 8 add up to 0, carry the 1. So 22 plus 28 gets me a 50. And we could check this thing here, right? This is, if I think about from my index for a second, I've got an index of 0, 1, 2, 3, 4, 5. So I've got 2 to the 5th plus 2 to the 4th, nothing, nothing, 2 to the 1, and then 0. 2 to the 5th is 32, plus 16, plus 2. Lo and behold, that works out to be 50. So again, when computers are doing addition, they are following this sort of algorithm because they are thinking, if you will, exclusively in binary. So this is, it's an algorithm. It's a process that has a rule, and we basically carry that rule for as long as we have digits. Once we run out of digits, we've gotten all the way to the left, we can finish here. Now, subtraction is going to work in pretty much the exact same way, but with its own sort of snag, because it's going to have to be what we do with normal numbers, but in reverse. So again, let's once more do a decimal number subtraction problem. So suppose we do vertical subtraction. You might be able to do this one in your head, or I know you can do it on a calculator, but that's not the point here. We're trying to learn how the algorithm works. So 304, if we do that minus 125, remember the way that this works is we look at the number here, 4, and we're trying to subtract 5. What's the problem, right? 4 is less than 5, so we're going to have to borrow from the preceding digit. In other words, we're basically going to have to make change. But we have another problem when we do that, right? The 0, we can't take any 1 away from that. So what ends up happening here is I'm going to borrow from the 3, right? I'm going to basically convert that thing into hundreds, right? So I'm going to convert the 300s, excuse me, I'm going to convert one of those 300s into tens. That's going to give me 10 tens. Now, one of the tens is going to have to go here, right? To borrow from the 0, I had to borrow from here. I had to take 100 converted into 10 tens. I set aside one of the tens for this, which leaves me with 9 tens right here. Once I've made change, I now have, this is the same number, right? This is really just 2 hundreds, 9 tens, and 14. That's the same thing as 304. Once I've done that, I now have numbers that are greater than the things I'm trying to take away, so we just do the subtraction. 14 minus 5 is 9, 9 minus 2 is 7, and 2 minus 1 is 1. Subtraction's a little trickier, so it's going to be the same idea in binary. So all of the stuff we mentioned about carrying, it's like that, but doing it in reverse. We start once more aligning the numbers vertically such that the rightmost digits are aligned with one another, and then we're going to subtract the columns vertically from right to left. And the key here is that if the number that we're subtracting is less than the number we're subtracting from, we have to borrow from the digit to the left. In other words, we have to convert that larger digit into a certain number of smaller ones. So let's think about what exactly happened when we did this, right? I was making change. This thing I know represents tens, so I'm going to convert one of those things into 10. So you can kind of think about it as that thing is really 10 plus 4, the way that we wrote it here. So what I'm going to do here is reduce that digit by 1, and then add 2 to the current digit. So I'm going to allow myself to use the symbol 2 here, just so that we can think about it a little bit more clearly, even if our answer isn't allowed with 2s. We won't need them when we get to the answer. So if we see the digit to the left is 0, then, like we saw here, we're going to have to continue borrowing further and further to the left until we arrive at a non-zero digit. All right, so let's do a quick exercise here. 101, it's not 101, I said it wrong. 101 minus 11. So let's start by aligning these numbers here with the rightmost digits aligned, and then we're going to do subtraction. So if we do 1 minus 1, we get 0. Now 0 minus 1, 0 is bigger, sorry, 0 is smaller than 1. So what are we going to have to do? We're going to have to represent this thing we know has a place value of twice as large as this one. That's the whole idea with the place value system, is every time you go one further to the right, the digits to the right have a value equal to the radix times as many, it's the radix times as many big as what it was, right? So in decimal, each digit to the left is 10 times as big as what it was. Here with binary, it's twice as big as what it was. So the way that we're going to do this here is we're going to cross this thing off. I'm going to write, instead here, I'm going to write it as 2, just so my brain can think about it. If you want, the technical way to do this would be to write it as 1, 0, and then subtract 1. But we can think about this with 2 for right now. If we do, so I borrowed from here, which means I have nothing left over, right? If I take away from that 1, just ends up with 0. I converted that thing here. I got a 2 minus a 1 is going to be equal to 1. Let's do a quick double check here, right? 101 is 4 plus 1, which is 5, and 11 is 2 plus 1, which is 3. And we can note that 5 minus 3 is 2, which in decimal is 10. By the way, let me go ahead and make sure I'm very clear about my numeration systems here. So yeah, we did get the answer that we would expect based on what we know about decimal numbers. Let's do one more exercise like this, slightly more involved. 1001 minus 1011. 01 minus 1011. Okay, so we start at the rightmost digit after we've aligned them vertically. 1 minus 1 will get me 0. And now I'm trying to do 0 minus 1. But that's not going to work. So I'm going to have to borrow from the preceding digit. Oh no, but this is going to take a little bit, right? So I'm going to borrow from the preceding digit. So that thing is going to get changed for a 2. But now this one's going to have to get borrowed from the digit before. Now I can't just write this thing as a 2 because I've already made the change. Think back up to this example, right? When I borrowed from this 0, since it had to borrow from the preceding digit, it ended up being 1 less than 10. That 100 got converted into 9 tens and 9 tens and then 1 10 for over here for that rightmost column. So the same thing is applying here. I have to borrow from the preceding digit in this sort of cascade, right? So I got to go all the way over to here. This thing is going to get changed down into 1 from there, 1 from here, and 2 from there. So once I've borrowed all of those things that I've needed, again, this digit is twice as large, so when I borrow 1 from this column, it's got twice the value here, and then I had to keep borrowing from preceding digits in order to be able to get numbers that are big enough to subtract. 2 minus 1 is now equal to 1, 1 minus 0 is 1, and 1 minus 1 is going to be 0, so all I'm going to be left with is 1, 1, 0. Let's do a quick double check as well. Right, 1, 0, 0, 1. Note leftmost one is the fourth power of 2, so 16. So that's 16 plus 1. And 1, 0, 1, 1 is 8 plus 2 plus 1 is 11. If I do 17 minus 11, these are both base 10 numbers, I get 6 in base 10. And we can double check that the number that we have here, 1, 1, 0, is 4 plus 2, which is in fact 6. So again, it's the same fundamental concept, but it's a little bit trickier because we are so used to thinking about things in a certain way. It's kind of like if you were to do this, just to do one last example, if we did the same exact thing, but in decimal, if I took the decimal number that had the same numerals in base 10, and I subtracted 1011 in base 10, how would we do that? Right? This is something we're probably more familiar with, in case this example was like, what the heck just happened? Right? 1 minus 1 would get me 0. Well, now 0 minus 1, I can't subtract 0 minus 1, so I have to borrow from the preceding digit. But that digit, I can't do that without borrowing from the digit to the left of that. And similarly, I can't do that without borrowing from the digit to the left of that. Now, each of these two digits is now going to be 1 less than what it was. Now in decimal, doing 1 less than the maximum is going to take me to 9, right? And then this thing here was really saying 10 plus 0. So I've got 10 minus 1 would get me 9, 9 minus 0 is 9, and then 9 minus 1 would get me 8. Right? So that's the same sort of idea that just happened here. The first digit that I'm trying to convert from a 0, I have to borrow and turn it into a 2. And then any subsequent digit that I have to borrow from in that cascade is going to get reduced to 1 less than the maximum until I get all the way to the largest digit that I have to borrow from, which just got reduced by 1. Hopefully that's making a little bit of sense. We're now going to do the same sort of processes, but in hexadecimal. So let's once more begin with a warm-up question and ask what hexadecimal numeral is going to be the successor to the hexadecimal numeral FF in base 16. So, well, let's think about, to answer that one, we first have to think F is the largest digit that can be expressed in hexadecimal. So if I take F and I add 1, right, remember F is 15. If I add 1 to 15, I get to 16. The way that we represent that in base 16 is we have to go to the next digit. So we put a 1 and then a 0. Remember, that's not 10, that is a 1, 16, and then 0 ones. So if I were to find the next digit after F, it would be, sorry, so it would be 1 digit. It would actually be represented by 2 digits. It would be the numeral 10. But now I would also have to do that, right? So then this next letter F, I'd have to have it go to its next maximum. So if we added 1 to that, it would then have to revert to the next digit up. So then if I take FF in base 16 and add this thing that we just said, excuse me, not that thing. Let me fix that. Right? If I'm trying to find the successor, I'm trying to add 1 to what I had. So this thing works out to be, we can think about F, let me split it apart. Right? FF is a 15 in the 16's place, if you want to think about it that way, and then a 15 in the 1's place. So I can write that this way. So that's this part of the number. If we add 1 to that, then what we just said is that adding 1 to F will get me 10, right? Because we ran out of digits to represent the numbers, we have to go to the next thing. And now at this point, we have to do the same thing with that second digit, right? When we take 15 and we add 1, we get to 16. So that means we're going to have to add another digit. We're going to have a 1 in the 16 squared place, and then 0, and then 0. So it's kind of like we did with binary, but we have to rethink about the fact that we have 16 different numerals to work with. So here's the process. It's going to look very similar to what we just did. Start by aligning the numbers vertically so that the rightmost digits are aligned, and then we will add the columns vertically from right to left. Now, one of two things is going to happen when we add 2 digits together. One option, so if you have, like, say, 3 plus 5, you just get 8, which is a digit that we know how to represent. Or even in hexadecimal, if we were to add, say, 5 plus 5, we would get 10, but in hexadecimal, that's A. We see that here in this table. 5 plus 5 works out to be A. But the other thing that can happen when we do addition is that the 2 digits, when added together, cannot be represented by a single digit anymore, right? We're very used to thinking about this like 5 plus 5 in decimal would be 10, which we have to have a new digit now. We have to have 2 digits to represent that sum. A similar thing is going to happen here. So for instance, if I add A, let me do a different one. Let's do the example we just did. If I have F plus 1 will get me 10, because I've ran out of digits here, right? In other words, it's saying 15 plus 1 is 16, but the way we write 16 in hexadecimal notation is with a 1 followed by a 0. You don't need to represent, or you don't need to memorize this table or anything like that. You can always think about sums in terms of the underlying number that is represented by these numerals. So anytime we get to a sum that is going to need more than 1 digit, we're going to end up carrying the 1, if you will, and adding that to the next column. We'll do one example like that. Find the sum E8 plus B9. So we'll start by aligning our columns here, E8 plus B9. So first off, we got 8 plus 9. Now, if I'm thinking about that in base 10, 8 plus 9 is 17, right? But if I'm thinking about representing 17 in hexadecimal, right, that is greater than 16, so it can't be represented by 1 digit. But we can think about that as 1/16 and then 1 left over. So we could write that as a 1/16 and then 1 left over. So how do I represent this sum now with this column? So 8 plus 9 works out to be 1 and then a 16. That 1 is going to have to get carried over to the next column. So in the next column, we're going to have to add E and B and then add 1 to that. So E plus B, if I just think about this again, you can go to the table on the preceding page, or you can just think about these things in terms of decimal numbers for a second. So E plus B, those are hexadecimal numbers. E is 14, and B is 11. If I add 14 and 11, I'm very used to doing this sort of stuff in decimal notation, right? That's going to be equal to 25. Now, 25 in hexadecimal, we know that that's bigger than 16, right? We can think about that as 1/16, and then the stuff that's left over would be 9. So we would write that as 1 followed by a 9 in hexadecimal. Good so far? Well, that's great, but you'll note that what I was actually doing is I need to add E, B, and 1. So if I take E and then add B and then add 1 to that, well, we already did the E plus B. We got 1, 9. So now I want to add 1 to that. If you want to write the 1 in the subscript, you can do that as well. So a 1 followed by a 9, right? If we add 1 to that, remember, in hexadecimal. So if I add the 1 to the 9, I don't need to carry anything because hexadecimal can write numbers up to 15. 1 plus 9 is 10, which in hexadecimal is A. So I can write this thing as 1A, base 16. So when I add 1 plus E plus B, I get 1A. Again, to show you how this would work in a slightly different way using the table that we had just a moment ago, if I want to think about E plus B plus 1 using the table, E plus B, let me find that, it looks like I'm in this row right here, right? E plus B is 1, 9, we just mentioned that. But if I want to add 1 more to that, well, I can just go 1 further spot down, we get 1A. So that's the basics for addition. We could also think about how to do this in subtraction, and the ideas are once more going to be the same basic principle. So we're doing subtraction just like we did in decimal or binary, which the fundamental idea behind subtraction is we're doing addition but in reverse. We're basically saying what number do I have to add to this thing to get that thing. And if we try to subtract a larger digit from a smaller digit, we have to borrow from the digit to the left, which may involve a sort of cascading effect as needed. Now, when we're doing subtraction, because subtraction is addition by an unknown number, we could consult the table that we had on the previous page to figure out what number do I need to add to get some desired given value. So let's look through a couple of examples, one easier, one harder. F3 minus 2D. So these are both hexadecimal numerals, clearly, dealing with A through F here. So I'm trying to subtract 3 from D. Well, clearly I can't do that because D is larger than that. So what we're going to have to do is we're going to have to borrow from the preceding digit. Now, borrowing from the preceding digit is going to make it 1 smaller. So basically, I'm changing this thing out. When we take away 1 from F, we get the next biggest hexadecimal digit, which is E. So then I'm going to borrow here and write that as 1, 3. So I've got E plus 1, 3 is the same thing as F3 because I've taken 1 power of 16 and converted it into the 1 so that we can make change. Again, let's go back to the preceding page for just a moment to remind ourselves how we did this, right? The reason I knew that this was 9 down here was we were trying to figure out 14 minus 5 is equal to blank, right? Whenever we have a subtraction problem, this is equivalent to saying 5 plus what gets me to 14. So we can think the same way here. I'm trying to figure out what do I have to add to D to get this number. So D plus what gets me 1, 3. Remember, these are hexadecimal digits that we're working with. 2 ways we can do this. 1, just thinking about what the numbers mean. 2, consulting the table. Let's consult the table first, why not? So we want to figure out what do I have to add to D to get 1, 3. Well, if you look at this column, this is the result that we get when we add stuff to D. So what do I need to add to D to get 1, 3? It looks like it's down here. That row coincides with the row for 6. So if I add 6 to D, I will get 13. I said 13, didn't mean to. 1, 3 is not 13. Let me revisit this now with numbers to think about this in terms of decimals for a second, right? D, remember, A is 10, B is 11, C is 12, D is 13. So this thing is, let me write it in words to avoid any potential weird ambiguity here. This is 13. If we add 6 to that, we know we will get 19, right? Well, what's 19 in hexadecimal? It's a 116 plus 3 ones, which we represent like so. Again, you can either think about it with the table, or you can think about it by doing some numerical reasoning, converting stuff into decimal. So anyhow, all of this was to say that 6 was sort of the magic number I needed to add to D to get 1, 3 out of it. So we're going to write a 6 down here. And now I'm going to subtract 2 from E. Well, that one actually can do, right? Because E is larger than 2. So I just have to wind down the digits by 2, right? If I were to subtract 1 from E, it would take me to the next smallest digit, which is D. And if I were to subtract another one, it would take me to the next smallest digit, which is going to be C. So there we go. There's my answer. My answer is C6 in hexadecimal. Again, that last step that I just did, another way to think about it using the table, E minus 2, I'm trying to figure out what, so if I'm doing E minus 2, I'm trying to figure out what do I have to add to 2 to get a result of E. Well, it looks like if I want to get a result of, let's go to column 2, and I want to figure out what I have to add to 2 to get a result of E, I got to go all the way down here to C. Right, so 2 plus C is what gets me E, which is to say E minus 2 is going to equal C. One last example here, doing the same sort of thing, another difference problem. We've got 9A17 in base 16 minus D3B. Well, note, there is only 3 digits in this numeral here, so let's go ahead and make sure we align the rightmost column here. So first off, I'm going to have 7 minus B. Well, B is bigger than 7, so we're going to have to borrow. How does this work? We're going to have to borrow from here. That's going to turn into a 0, and then we're going to put in this extra 1 that's right here. So we're trying to figure out 17 in base 16 minus B. So in other words, we're going to have to figure out B plus something gets me 17. Let's go back and consult the table. What do I need to add to B in order to get a result of 17? Looks like it's down here. So I need to add C to B in order to get a value of 17. So that means 17 minus B is C. Again, quickly doing a numerical decimal check, right? 17 in base 16, or actually let me check the addition thing here. B in base 16 is 11. C in base 16 is 12. That's going to get me 23 when I add those two numbers together. If I want to represent 23 in hexadecimal, hopefully you've done the homework from last section, because otherwise this stuff doesn't make a whole lot of sense. If I want to represent 23 in hexadecimal, I can do 116 and with 7 left over, so 1, 7. All of this is to say, when I do 1, 7 and subtract B in hexadecimal, I get a result of C. Going on to the next column, I have to do 0 minus 3. Oh no, got to do it again, right? Now, what's going to happen here? So I got to put the 1 in front of here, and I'm going to have to borrow from this digit, A. Well, the A is going to have to get reduced by 1. Remember, A in hexadecimal, that's the first digit that we can't represent with our normal decimal numerals, so that's worth 10. So we're going to have to take away 1 from A. When we take away 1 from A, because that represents 10, we write 9. 10 minus 3, well, fortunately, we actually know how to do that stuff. Doesn't take any fancy math. Nope, I lied. Got to redo that. I just made a mistake there. Mistakes happen. Let's try that again. Because remember, this one's not 10. This one represents 16, and then 0, right? So this number here, we have to keep in mind that we're representing a hexadecimal numeral here. So when we take 1, 0, and we subtract 3, that's really taking 16 and subtracting 3. Well, if we take away 16 minus 3 gets me 13. So when I do that in hexadecimal and I subtract 3, well, we can represent that using a single hexadecimal digit, right? 16 minus 3, if we're thinking about it in terms of decimal, is 13. And the way we do 13 in hexadecimal, A is 10, B is 11, C is 12, D is 13. Or, again, you can think about this on the preceding table. What do I have to add to 3 to get a result of 1, 0? The answer is I have to add D. So we put a D right here, and then keep going. We gotta go to the left here. We're trying to do 9 minus D. Once more, we're gonna have to borrow. Since D is larger than 9, we have to put the 1 here and borrow from that. Now the 1, like a mistake I made on the previous example, actually corresponds to 1/16, right? Because this digit is 16 times larger than this digit here. So we're trying to do 19, actually 19, but 19, represented in hexadecimal, and subtract D, represented in hexadecimal. So we want to know, again, what thing do I have to add to D to get a result of 1 at 9 in hexadecimal? Let's go back to that beginning page. D plus what gets me 19? So D plus, it looks like C will get me 19. So that is to say, when I do 19 minus D, the result that I get is going to be C. We're almost done. The very last thing here, we know that we don't have any more digits to take away, so 8 minus, well, nothing is going to get me 8. All right, so this stuff, it's a little trickier, right? We're taking things that are very familiar and making them very unfamiliar by changing the context. So we have to think about this stuff very, very carefully and really delve into our understanding of how these algorithms work. In the next section that we're going to do, we're going to explore a few applications to some of these things. So I'll see you soon.